systems and the history of the energy systems. And without any further ado, we start with the first talk by Astrid Kander on the history of the energy transitions. And I'll be in charge of paying attention to time.
Yep.
And
Okay.
so you have about
Does
45
this work?
minutes.
Do you hear me well? Yeah. Great. Thank you very much for your kind invitation to let me speak here. It's a pleasure to be here and to meet with so many physicists. I've never met so many physicists at the same time in my life before. And one thing I find particularly interesting is that physicists argue and discuss just as much or perhaps even more than social scientists and economic historians. And I thought in physics or science things were so much more clear and everybody agreed, so I'm really surprised and it's very interesting to be here. Okay, so I will talk about my favorite topic, which is historical energy transitions today. And ever since I wrote my PhD thesis in 2002 about the energy history of Sweden, I have worked in this area, and now I will tell you more about the energy history of Western Europe. So if we think about the usefulness of energy history, many of you here, you try to work on the present day and look forward into the future. What I do is in a way simpler because I can look in the past, but to things that really already have happened. So it is like evidence of behavior in a non-simulated setting. You know actually what happened, but you do not always have the data for that allows you to assess what really happened. What is possible and useful also is that you can have a long time perspective and you can thereby identify trajectories in development. For instance, path dependence of individual nations' energy histories and so forth. The third thing you can do is that you can examine energy consumption in relation to other variables. For instance, population, technology, GDP, and we do a lot of that. Look at trend and trend breaks and so forth. One way of looking at historical energy transitions is simply to look at the shares of different energy carriers in the energy system. This is a graph of the share of different energy carriers in a set of 8 Western European countries together with US and Japan, 1800 to 2015. And here we see that in the around 1800, roughly 50% consisted of fuel wood, and then food for people and food for the animals was also a substantial part. Coal had already entered the scene in 1800, but it was very much located to one particular country, which was Britain. Then gradually the coal transition took place. We can see the large dominance of coal, and then after the Second World War we see the oil breakthrough, and we also see from 1970 onwards we see a diversification of the energy system with nuclear coming in, more of natural gas and so on, which is related then of course to the electricity system, because you can use any kind of primary energy to produce electricity. I have, together with 2 other authors, Paolo Malanima and Paul Ward, written this book for in the Power to the People, Energy in Europe over the Last 5 Centuries. It came out at Princeton University Press in 2013. It's like 500 pages, and I'll try to summarize it in 30 minutes. It's not going to be that simple, but I'll make a bold attempt to give you the broad story. I cannot go into the details and not in the special geography of the individual countries and so on that we do in this book, but I will give you the overall picture. So the motivation for the book is of course the challenges we're facing today with global warming, also the discussion of peak oil, and the need we have to make a big transition today. So is there anything that we can learn from previous transitions, or what can we learn from them? We were a group of people, and we worked very hard for many years to produce this graph. And this graph is a graph of energy per person per year in these West European countries, 8 countries. And it may seem like a simple thing to do, but it involved a lot of data mining, collection of statistical sources, but also making small models of things which you couldn't really find easily accessible data of. For instance, draft animal muscle power. You could find data of the actual numbers of animals, but then you needed to make estimates of how much did they eat, how much did they weigh, how much did they work, etc. Firewood was even more tricky.
What are the units?
It's gigajoule per person per year. Sorry, I missed that. So every good book should have some kind of plot, a red thread and a mystery that is supposed to be solved. And the mystery here in this graph, we think, is what happened after the 1970s. There are many mysteries, of course. You can say one mystery is also what happened in the pre-industrial period between 1500 and 1600, because there actually per capita energy consumption went down. Anybody who knows why? It was actually because there was this little ice age, so the climate cooled down, so it couldn't produce as much food and firewood and so forth. So then we have the increase. We have a period of stagnation in the 2 world wars and the interwar period. And then we have a really rapid increase after the Second World War, which then reached levels out around 1970. So per capita energy consumption around 1970 levels out. So why is this? I don't need to speak to physicists about what is energy. I just wanted to say what is included in our accounts. We include both traditional energy carriers like food, fodder, direct working water and wind, firewood, peat. We also include the more modern energy carriers, coal, oil, natural gas, nuclear power, hydroelectricity, solar electricity, geothermal and wind turbines produced electricity. So all that is included. There's a lot of discussion in economic history if the Industrial Revolution was something that happened gradually or something that had more the appearance of a revolution, something that was very drastic and a non-linear increase. And if we write economic history from the energy side, as we do in this book, it's very clear that it's quite dramatic increases and changes that take place during the Industrial Revolution. We have divided it, we have put a filter on our graph here with an interpretation of it in relation to economic history, which means that we have one period which is the pre-industrial period. About 1/3 of the book is devoted to that. I will only say very little about it. The first Industrial Revolution is the second half of the second part of the book, and the second and third Industrial Revolution makes up 1/3 roughly of the book. But I will devote more time to that in my talk here. You see, I've also indicated some what I call development blocks here, and that is the coal, steam, iron development block, the internal combustion engine and oil development block, the electricity development block, and the information communication technology development block. These are like centers or cores of the industrial revolutions that we are seeing in this period, the first, the second, the third industrial revolution. The concept of development block was first coined by Erik Dahmén, a Swedish economist. It resembles many other concepts like large socio-technical system that Hughes used, Thomas Hughes, and also technical innovation systems that some people work with that concept today. But I think this one has other features to it, which is why we prefer it. I will come back to that. So the development block is always centered around some macro innovation. Could be then the steam engine or the internal combustion engine and so forth. And then, of course, in order to make this transform society, a lot more of complementary activities and resources are needed. And that is what is indicated by this very simple graph here with energy, finance, institutions, firms, entrepreneurs, knowledge and competence, infrastructure, all that needs to be put up and come into existence to make this macro innovation really have a profound impact on society and cause some kind of industrial revolution. In the organic economies or the pre-industrial economy, there were two basic constraints that are related to energy. One was the land availability, which was limited by the surface of the earth simply. And since everything was more or less coming from the produce of the soil, there was a competition over this scarce resource in the pre-industrial society. People needed the soil to grow firewood, to burn for their household cooking and heating in the cold countries, but also to make charcoal that could be used to produce iron, for instance. So there was and everything, textiles and everything, basically needed land. And so there was a competition over this scarce resource. The second constraint was the low power available for people. Basically, what was available was their own draft or their own muscle power and animal draft power, and a little bit of direct working water and windmills, but they were not very powerful. Maybe a few horsepowers up to maybe 10, 12 horsepowers in case of a big water wheel. Those two constraints, they were both broken during the first industrial revolution with the employment of coal, which of course freed people from the land constraint for producing energy, because you could dig down into the earth and get all this stored fossil energy out of it. And the low power was broken by the steam engine that for the first time in history allowed people to do one kind of transformation that had not been possible before. In the pre-industrial society, these were the kind of transformations you could do of energy, but you could not close that circle. You could not make heat into motive power. And that was what you could do with the steam engine. This is just illustrating what I said before, that there was a drop in temperatures in the 16th century, which meant that and power is, as you as physicists are well aware of, energy concentrated in time and space. So it's issue of quality as much as quantity. It's energy density, it's sustained effort. It was the ability to do new things as well as more things. So, for instance, transport things much faster than was ever possible before. And here is just some illustrations, like a horse, 1 horsepower. Here is a rocket which has like 160 million horsepower, just to illustrate the big leaps we have made in power. So the first industrial revolution and the coal transition in 19th century Europe, it was above all the story of coal and what people were able to do with coal. So some people have even claimed that the steam engine was in history the most important innovation ever made. It equipped people with, for the first time in humankind, inanimate energy slaves. You only needed to feed them with some coal and they would do a lot of work for you. And this caused the Industrial Revolution. It made people, if you speak about production factors, it meant that a capital deepening effect in the economy. So laborers were equipped with much more capital, particularly machine capital, and they could be much more productive. The steam engine was not just finished at once. It had a long development with many steps before it could really be employed for producing things in the textile industry, for instance. The first steam engines were extremely inefficient. The Newcomen steam engine had 0.7% thermal efficiency, and it could only make an upward and downward movement like this. So it was not smooth and it was not rotating. So that was not possible to use, for instance, to produce clothes. But it could be used to pump water out of the coal mines themselves. And there was also where you had access to this extremely cheap coal, which was necessary to power these engines because they were so inefficient. You couldn't afford transporting the coal anywhere else. So this was the ground for the steam engine. So this I already said. We know that Europe has quite a lot of coal deposits, but they are not evenly distributed. It gave some countries more advantages than others in accessing this coal and getting onto the Industrial Revolution. Here is a map of the coal fields. We see that particularly Britain was well endowed, but also France and Germany, Poland, and some other places. But some countries almost lacked it entirely, like Italy and Sweden and Norway and so forth. So this also meant that the coal transition was not an even event. It didn't take place at the same pace or to the same degree in the different nations. This is the set of 8 European countries we have included in our book, and you see that by far Britain has taken the lead here, has already in 1800 covered almost 80% by its primary energy use by coal, while the other countries had hardly started using coal at that time. Some of them that had their own domestic resources, they more or less caught up with Britain over this 100 years or so, not quite, but almost. But the countries that did not have domestic coal, they never got as much of their primary system out of coal as these leaders. You can also see that if you study economic history, you can also see that this is pretty well correlated with the economic growth of these nations. Britain took the lead and then was followed by Germany, France, and so on. So it had a strong relation with the energy consumption. One concept that Erik Dahmén uses in his development block idea is the 2 concepts of market suction and market widening, and we use it throughout this book as well when we try to explain how the different transitions took place. Market suction means, as it sounds, like something is hoovering or sucking the market for complementary resources. Market widening is a supply side effect where the price has fallen enough to enable usage in new areas, which was not perhaps the core or key area where this complementarity was so strong to start with. So if we look at the coal transition, it started with a market suction process with steam engines, of course, being best run on coal, especially when they were so extremely inefficient. They could only be placed in that mine. Also in iron making, coal became a possibility, and there was a demand for coal for the iron industry. This enabled a much cheaper steel making and also cheaper steam engines, which meant they could be employed in transportation, long distance transportation, for instance in railways and in steamboats, which made coal able to transport itself out to the customers. So that is where the big transition really came in Europe. That was when the coal was able to transport itself out cheaply to the customers. Then we could have a coal transition also in Sweden, in Italy, and countries that didn't have this resource at all. So you could summarize it like this, very simple graph here. Steam engines, market suction for coal, transport revolution, market widening for coal, and that goes for then the industrial society. No, okay, so I still have quite a lot of time.
20 minutes left.
Thank you. Once I got a question by somebody from this institute, IASA, that Bob Ayres mentioned the other day, when I was talking about these ideas, and I was presenting our series of the historical energy transitions. It was somebody called Silverberg, I think, and he was very astonished that the diffusion curves of these energy carriers did not follow any smooth, logistic S-shaped curves. And my idea, when I didn't have a good answer at that point, but I think that it has to do with this. Both the thing that in one big development block, say for instance the internal combustion engine and oil, we have several smaller development blocks inside that you spoke about yesterday. We have the development block around the car, we have the development block around trucks and buses, and later on airplanes. So they all have their different diffusion curves, but even more so, I think it's important to realize this thing with the market widening, that eventually the new fuel becomes so cheap that it becomes affordable for all kinds of usages, not only where it's strong complementarity. So the second industrial revolution is very much to do with oil and electricity. And this also meant, because of the electricity breakthrough, it also enabled the diversification of energy supply after, especially the mid-1970s, after the oil crisis. Different countries took different roads in Europe. Some went more for natural gas, the ones that had found it in the North Sea, and others went more for renewables, and some choose nuclear power. I'm not going to say so much about that, but there is an internal logic, as you know, as physicists, you know, there is an internal market logic of electricity system expansion, which you could also call market widening, because it's best to have simultaneous production and consumption. They should be balanced, and that is best achieved in a very big system, a very big grid. And that is also what has taken place over the years, that Europe has become much more integrated, even across nation boards and so on. This has also lowered the price of electricity. Here we see the lower price of electricity indicated here, how it has really dropped substantially and enabled the use for lots of new things. We can also see that the two phases of electrification in Europe follows two different phases. One was where electricity basically replaced already existing technologies. For instance, a cooking device that was previously maybe using gas or was using firewood could now be replaced by an electric stove instead. The first phase was also had a very strong urban bias. It was the cities that were electrified first. It had some impact on productivity in the factories, but to start with, the electric engine simply replaced the steam engine in the factory, and you kept all these complicated shafts and wires, and if the engine broke down, the whole factory stood still. Later on, this became much more efficient with first a group drive, one electric engine for several machines. Later on, it was a single unit drive where you had one engine for one machine and then integrated, so we don't even see them these days. So in the second phase, electricity started to be used for entirely new applications. People came up with new ideas, for instance, the vacuum cleaner or something like that. And we could spread it to the rural society by expanding the grid, connecting different parts of the country. And it also had a much more productive impact on factories and energy productivity in industry. I will now shift over to the rise of oil, which you know that Europe did not have, when the oil transition started, any own deposits of oil that they had discovered at that time. So they had to import it. Later on, some were discovered in the North Sea, but that came much later. So the rise of oil in Europe, it was all due to imports and the price of transportation. And it all came pretty much suddenly after the Second World War. You see very small changes taking place before that. One thing here we can see when it comes to path dependence is that the countries that had gone very early for coal and had built up a lot of capital using coal, like UK, for instance, they never had a strong oil transition. While other countries had a much more, like Sweden, for instance, had much more of a drastic oil transition. So what did cause this oil transition? Can we see some similar pattern as we could see with the market suction and market widening for coal? Yes, I think we can, because of course there was a complementarity between the cars and gasoline, or cars and diesel. They needed it to run. But what was even more important in the longer run was that we also saw a transport revolution here with much bigger oil tankers. And how were these oil tankers powered? Yeah, they were powered with big series connected diesel engines. So here again we have the internal combustion engine acting both on the demand side and on the supply side. So it opened up the possibility to use oil for a variety of different appliances. For instance, even such a wasteful thing that we think today, at least, as household heating. That became very prominent in certain countries, like in Sweden, for instance. A lot of people heated their houses with oil. Here we see this illustrated, the big oil tankers and the price of oil. This is not the actual price of oil, but this is the transportation share of the price of the landed crude oil. And you see it was roughly 50% or so that depended on transportation costs. So it really mattered where you lived and how far from oil resources you lived. But these days now, it's just a fraction. It's only a few percent. It really doesn't matter where on the globe you live. You have access to cheap oil anywhere.
That's a European average?
No, that is...
world average?
Yes, I found it in a book which was world average. Yes, and so again, we can see this pattern here of market suction and market widening also in these three development blocks that are making up the second and third industrial revolution, with market suction, market widening, and then the real establishment of the core technology. I will now jump to the third industrial revolution and the higher energy efficiency in late 20th century Europe. This is what I said was the mystery or the puzzle we needed to solve in this book, right? And you see at the upper right panel here, you see an IPAT decomposition of the energy in Western Europe, 1870 to 2005. So the annual increase in energy was 1.5%. The increase in population was 0.5%. Income per capita increased by 1.7%. So what counteracted this was improvements in energy productivity, or if you turn it the other way around, a falling energy intensity curve of minus 0.88% per year. But this wasn't evenly distributed over this long period. So if you look at the different periods here, you see that between 1970 and 2005, we had the most drastic decline in energy intensity. And we think that this has a lot to do with the story of ICT and energy efficiency. And how is that? Yes, well, one thing is that also here we see a similar story as in the previous development blocks, but as José told us the other day, this is really of a different magnitude and scale, how this price decrease has taken place compared to the other market widening aspects of the other development blocks. This is just indicating the fall in prices over 10 years, but that has continued, yes. So what is the reason for the trend break in the 1970s? Well, as a good scientist, you shouldn't just grab hold on one explanation and then just argue for that. You should look into various options. And we have looked into these 4 candidates: transition to the service economy, structural change of the economy, which means it will need less energy, or it was this more the technical side of the manufacturing industry that changed it with the ICT revolution, or was it maybe the oil crisis with a higher price of energy, or was it simply a very bad news in that case that Europe was simply moving the problems away to somewhere else in the world by their foreign trade, so that they were exporting more light products and services and then importing more heavy goods. Well, one indication that it's ICT is behind the trend break in the First, I'll say a few things about service transition and energy. I have written quite a lot about this, and in ecological economics, 2 publications, Baumol's Cost Disease and Dematerialization of the Economy in 2005, and together with Sofia Henriquez in 2010, The Modest Environmental Relief from the Transition to the Service Economy. In both these publications, we show that in real terms, the transition to the service economy is largely a price illusion caused by what is called Baumol's cost disease, that industry is much more able to increase its productivity than at least personal services is. You can just take a very simple example. Think of a concert pianist, or think of a psychologist who is listening to their clients. They can't really speed up their work without destroying the quality of it, right? So because the human time and presence is a prerequisite, and it's like part of the product itself. So that's the logic. You cannot really replace people in these kind of services. Then Baumol has also realized that it's not as simple as that stagnating service sector and progressive manufacturing industry. There is also something in between, what he calls the asymptotic stagnating economy, which is a large fraction and a growing fraction, I would say, of the service sector, like the business close service sector, is now more and more taking on ICT and digital solutions and replacing people. But that's a little bit of a it's a mid story, but it's still if you this gives as a result is that the prices of services go up compared to the price of industrial goods, and also that you, because of the much higher productivity in industry than in services, you need to move people out from the industrial sector into the service sector, and that is what we have seen over the last couple of decades. But still, what we are really good at producing in our world today is manufactured goods. We are not really efficient in producing services. We are still pretty slow in that, because I cannot go into all the details of this, but we can maybe come back to it in the discussion. But in any case, this could not impact energy productivity very much, and it doesn't either if you look at it in constant prices, the shares of the different sectors. The service sector doesn't really grow much over 200 years at all, if you look at it in constant prices. If you look at it in current prices, it's a different story. But then all inflation is taken into account, and you never take inflation into the picture if you talk about growth, because then you're clearly exaggerating growth, right? So you shouldn't do that when you talk about this either. So one indication that it's ICT behind the trend break in the 1970s. This graph is not mine. I have stolen it from the work of Benjamin Moore, Fridolin Krausmann, Nina Eisenmenger, and Heinz Schandl, I think it was. And they have shown something very interesting here, which is, sorry, what's happened now? Oh, it's only happening here. Not here. Good. They have shown that if you look at not primary energy, but you look at the useful energy, what happens is that the useful energy in relation to GDP grows and grows up until roughly 1970. Then there is a trend break. It falls. So what does this mean? Well, it means that the economy is growing on basis of something else than energy services. It doesn't mean energy services becomes useless or you don't need them anymore, because you need them to sustain everything you have already produced in the economy, all the cars and everything. But the new things that are growing really and makes the whole economy grow, that's basically ICT stuff, and that's much more information based than it's based on energy. Yes.
A world average of that, would you find the same trend?
Nobody has done it, so I can't say. I would like to see that. It's a quite heavy work, as Bob Ayers knows as well, to produce this series of useful energy. So it has not been done. I have only 5 minutes left, so I will need to skip or just take it very quickly. I wrote another piece that supports the same story, basically, that there is a shift in the driving forces of the economy from, in this case it was 1950, but here it was 1970. I started a collaboration with an economist in Australia called David Stern. He found in my PhD thesis something which I think may intrigue you here as well, which is that the cost share of energy in the Swedish economy has fallen quite drastically over time. From, if you count the cost of collecting like firewood and all that, and grow food and so on, not all of that was marketed. You didn't sell all the firewood on the market, but some of it was sold, so you could estimate the price of what was not sold as well. And then if you take the cost of all that energy and you divide it by what was put on the market, that is GDP, you get this ratio. So it was almost as big as the total value of the output in around 1800. If you instead, you could also you could also add that to the GDP, and then you get roughly half of this result. But in any case, this is not consistent with a conventional growth model, a Cobb-Douglas growth model, because that assumes a constant elasticity of substitution of 1, which means you can always move. And if something becomes cheaper, like in this case energy, you would use more of it. And that means that the cost share would remain the same. And so this was something that was at odds with this model. And we therefore produced another model, and where energy is not something you can do without. You cannot substitute away all energy. So it is a constant elasticity of substitution model with less than 1. So we find that as expected here, the period 1850 to 1900 was very much driven by energy, but the period 1950 to 2000 was much more driven by capital and labor augmentation. Then we can discuss this thing about energy expanding ICT or energy saving ICT. We heard yesterday it can also expand because there are so many gadgets out there. But it also has a strong potential of saving energy, both in old traditional industries where you fine-tune the material and energy flows, and you also change the structure of the manufacturing industry. So you have more light industries in it. So it's more pharmaceuticals, more software and things you produce that doesn't require as much energy as to produce cars or things like that. So so we think that we have, I'm running out of time, so I have to, so we think we have solved the mystery, that it's ICT. Oil crisis also played a role, especially to save energy in houses. Service transition played some role, but not as large as believed. But maybe it will turn out to be more complicated, and that it has to do with all the international trade and outsourcing, and that is what I have been doing over the last couple of years with some people, and I intend to do also now in the future. So I cannot, I think, talk more now, so I will simply have to, I would just like to show you one final graph here. So the industrial revolutions and development blocks, where are we now and what can we expect for the future? If we look at it, every industrial revolution has unfolded over roughly 100 years or so. So when it comes to the third industrial revolution, we have basically only seen half of it. So there's another 50 years to come, and we don't know really what this will entail. Some people think that we will have lots of artificial intelligence, and they talk about avatars, and they talk about all kinds of things. But for me, when I look at the energy side of things, I cannot see us building up with all the constraints of going to a renewable energy system. I cannot see us building up a huge stock of technomass in our societies at the same time as we preserve the 9 billion people as we have today. I don't really see that, but maybe you think differently. Okay, that's my talk.
Thank you so much.
This was a very exciting talk, and I already have one question up here, Carrie.
Yeah, you should go with the mic.
To run up there.
That's your job.
That's my job.
Thank you, Astrid. Carrie King. So could you, I guess, maybe elaborate more on why you think ICT is responsible, or what percentage or what relationship? Because it's hard for me to separate the use of ICT from an increase in cost in oil. How would you know that how would you know the use of ICT after the 70s wasn't because we couldn't just keep drilling cheap oil wells? If we had a lot of still cheap oil wells and we had ICT technology, would we have just not used it very much because we didn't have to, right? The idea of energy efficiency really didn't exist before the 70s, and are you claiming that ICT is part of efficiency and would have happened anyway, or if we didn't have a restriction in oil, we would have known how to do it, but we just wouldn't have done it.
I mean, it's really, I cannot give percentages of these different explanations. They all play some kind of role in this story. I'm not saying that oil crisis didn't matter and the rising oil prices didn't matter. They mattered I know they mattered because we can see where did these energy savings take place. I didn't show you here, but we can see that it took place primarily inside the household sector with much better insulation of houses and so forth. It also took place inside the industrial sector. And there it was both due to efficiency increases in the old traditional industries that could be also somehow related maybe to saving oil, but also it had a structural effect inside the manufacturing industry where we saw the emergence of more lighter industries like pharmaceuticals, for instance. But I cannot give percentages. No, it's impossible.
Thank you very much for this historical presentation of transition full of learnings. And you presented the story with the evolution of energy, wood, coal, petrol, gas. But there is another way to tell the story, and it's through the energy carrier. At the very beginning, the energy and the carrier was the same. And with time, we have a sort of divergence between the energy and the carrier. And at the end of the story, with electricity, is only the carrier.
Yes.
Whatever will be the energy in it, you know. And this is very interesting because what is important is the carrier which can make the energy possible or not, and in order to transport and even to transform and to reduce the cost of such phenomena. Like efficiency, for example, is a part of the carrier for me.
Yes.
And the question for me is interesting because what will be the next carrier? And the next revolution will depend, in my opinion, of the next carrier. What will come after electricity? And one piece of the solution could be the light. You know, and it's because of that I think it's so important to think about artificial photosynthesis, because the key question is how to harvest the light and to transform and to transport and transform that in any useful energy we need. And you know this famous story, when we ask children where is the electricity coming from, the answer is from the wall.
Yes.
And perhaps the same children will say in the future, where is the energy coming from? He will answer, idiot, it will come from the sun. That's it.
Yeah, that's a more. I don't need to answer. It's an interesting perspective. Thank you.
Yes, I'm here on your left. Hello. Yeah. So now, first, I just wanted to thank you and your colleagues for doing all this hard work on the historical time series that a lot of us are using. Please keep doing that. It's really great. And secondly, I had a question about national accounting. There's a lot of effort being put into making the energy indicators better. Now we're looking at useful work. You're extending energy time series back. But I see very little attention being brought to GDP. And for instance, here on this graph that you have here, I wonder how much is changing or how good is our GDP accounting here? How can we account for what's really going on in the economy, and how does that influence our ratios there? You know, there's the sort of politically important example of banking, of course. You know, the UK has a very large banking sector, and and this is also in the 1970s. Banking is deregulated, international capital flows, so banks grow. How does that impact these series? And you know, I don't think we're putting a lot of attention on that. I was wondering what you're thinking.
I think that I'm a very rare economic historian because I pay so much attention to energy and energy accounting. Most economic historians, they only deal with GDP and improving GDP measures. So there's a big group of scholars in economic history called the Madison Group in the Netherlands. They are working together a lot on world GDP, on different countries' GDP, trying to make it homogeneous. It's also available on their website. You can find all that. So it's continuously being improved. There's a lot of debate going on when it comes to the history of economic growth and GDP. Some of the things you mentioned here are not so easily solved, and they have to do more with the more contemporary period where we have a lot of improvement in the quality of goods. Like, for instance, some people say that we are severely underestimating the role of ICT in the economy because the productivity increases due to ICT. We haven't captured them very well because the prices have fallen so fast that we have a problem of constructing good price indices. So they talk about making this other kinds of price indices, but on the European level they have had experiments in this respect, but they haven't agreed on it, how to make it. So I agree, there's a lot to do there as well. Yeah.
Another question?
Yes.
Okay, thank you first for this very nice and inspiring talk. Could you show again your slide, your mystery slide, one of your very first slides, please? I've got a question related to the pre-industrial period.
Yeah. So many slides.
Long time to go.
Long time ago.
Yeah.
It was very early. It was
very early. Sorry. Okay, very good.
That one.
Thank you.
Huh?
Well, that's related to the pre-industrial period. I mean, the 18th century, the Enlightenment age. I mean, I'm a bit astonished. I mean, that was a time where we had a growth of population. There were less great starvations as in the preceding, to the best that I remember, compared to the preceding centuries, such as 17th and so forth. And if usually when you have a growth of population, at least it was in Europe, at least in France, I remember was the case, and I guess it was also the case in all Europe, I would have expected that you see some kind of a change in this graph. And you barely see anything. The first bump that you see is around 1830. So how can you, what about Enlightenment? It changed the ideas, but not really, you know?
It's the units a gigajoule per person per year. The thing is that for this period, we basically only have good, really proper data from 1800 onwards. So what is done before that, it's Paolo Malani has made quite bold conjectures based on some kind of bottom-up modeling and taking some of these temperature variations into account, but it's really, really very rough. Yeah.
Thank you.
Yes.
Quick comment on the efficiency. One of the noticeable things is that efficiency of electric power generation increased rapidly before 1970 and stopped increasing. And much the same with internal combustion engines and so on. So that's a puzzle.
Why it has stopped increasing.
Also, I want to know where you got your useful work data.
I told you. I got it from that article with Benjamin War and Nina Eisenmenger and Fridolin Krausman.
That's what I was afraid of.
Were you afraid of it? Wasn't that good enough?
Well, let me say, it badly needs updating.
Oh, okay. Yeah. Well, I'm keen to see any updates.
Get any support to do it, though.
No, it's really difficult. I mean, we didn't, when we worked on this, gathering this data for the book Power to the People, we basically did it without getting any funding. Once we applied for money from the European Science Foundation, and we got rated as number 2, and they said, oh, this is a really good project. It's really worth being funded. But these researchers, they are so crazy that they are going to do the work anyhow, so we don't really need to fund them. And they were right. We did it.
Thank you very much for your talk. I liked it very much because you introduced thermodynamic machines, which started actually the growth. So this shows that thermodynamics really plays an important role in economics. And I think the question about the ICT can perhaps be answered by the first law of thermodynamics. If you say heat is equal to energy and work, you ask for the value of work, then this is energy minus heat, and heat is TdS, is entropy. So entropy, and in this means in economics, it means the worth of labor is first the energy and then standard of living times entropy. And at low standard of living, the energy was the most important part in working and achieving that. But at higher GDP, the standard of living rises, the T rises, and the influence of entropy, of knowledge, of ordering, of this is connected to ICT actually. Okay. Computers are just ordering. These are, in French they are ordinateur. Yeah. And I think at higher standard of living, ICT comes more and more into action. So this would explain then why this is such an important part nowadays.
Thank you.
So thank you very much for this great and inspiring talk. And let me take my prerogative as the chair to say one thing at the end. I actually 100% agree with you. What concerns me, that this information transformation has allowed us to get very much more efficient because we create lots of services by machines which just crunch information. They are now starting to actuate real things. They are moving cars, they are moving equipment, and I would argue that will cause an energy influx of enormous use, because suddenly I can do, these machines will do things and they will spend energy on their own.
Yeah, that's a risk. That's what I'm afraid of with this new phase of the ICT revolution.
Well, thank you very, very much. And we now get into